A very good morning to all. Today I am going to start a new topic that is called a rapid tooling. Last time we have seen different types of popular and commercial process and methods of rapid prototyping, and this is the further part of the rapid prototyping. This is called the rapid tooling. Okay. Then what is the why we are required rapid tooling? Unfortunately, with the rapid prototyping techniques, there is a only limited range of the material form which prototype can be made. Consequently, although visualization and dimensional verification are possible, functional testing of prototype often is not possible due to the different mechanical and thermal properties of the prototype compared to the production part. So that is the major problem over here, due to which we require rapid tooling. Refers to the mold cavity that are either directly or indirectly fabricated, or we can say manufactured, using the rapid prototyping technique. Okay, in this case we are manufacturing the die or cavities or mold, and from that mold cavity and dies we are developing a number of prototypes. Okay, because in case of prototype we have seen a number of method, and from that method and the processes, if we are going for the commercial purpose, sure we will get a number of product, but if we will require a high demand of product, that is only possible by use of different types of cavity and mold, and that is only developed and fabricated by use of rapid tooling. This is are the primarily used to create the multiple prototype, and rapid prototyping techniques are not economical when more than one prototype need to build for the same component. Hence, in this case, we require rapid tooling. In the rapid tooling, we develop by the different types of method, as already I discussed, like indirect or direct method. We develop different types of mold and cavity, as well as different types of die, and that die we will use to make the number of prototyping. Okay, means for we can go for like a batch production also, we can go for the mass production also. Now, what are the different types of methods in case of rapid tooling? There are the two methods. Okay, the first is called the indirect rapid tooling method. The second one is called the direct rapid tooling method. Okay, in this case, the first is the indirect rapid tooling method. Pattern is created by the RP. First, we will create and develop the pattern by use of rapid prototyping, and pattern used to fabricate the tool. For example, pattern for the sand casting and investment casting. Okay, we develop the pattern, and after developing the pattern, we can go for the mass production or as well as the batch production. We will develop the electrodes for the electrode discharge machining. Okay, EDM. We can develop the different types of electrode. So this is comes under the indirect method. If I'll speak about the direct method, in the case of direct method, rapid prototyping is used to make the tool itself. Directly we are developing the tool by use of direct method. Okay, so this is like a direct method. Importance of the rapid prototyping, rapid tooling. First important, tooling time is much shorter than for our conventional tool. Okay, in this case, we are developing a directly tool, and that will take a less time comparing to the conventional machines. Tool costing is much less than for the conventional tool. Tool life is considerably more. than for a conventional tool. Tolerance are wider than for the conventional tool. So this is our four advantages, and easily you can remember regarding the time, regarding the cost, regarding the life, time, cost, life, and tolerance. Okay, so this is like a four importance, or we can say advantages of the rapid tooling. After that, we are having, there are the two types of tooling. One is called a soft tooling, another one is called hard tooling. Okay, soft tooling is made out of silicon rubber resins, and due to its flexibility it is called the soft tooling. Okay, because of flexibility we are using the silicon rubber, then it is called the soft tooling, also called as the silicon rubber mold. Okay, because in this case we are developing the mold. We will see in the video so that your concept is more clear in the next slide. Okay, a silicon rubber mold is used to produce the plastic prototype components. Okay, but in case of soft tooling, always we are developing a mold, and that used for the plastic prototype, for developing of the plastic prototype, not for the metal. And in the some cases wax pattern also for the further investment casting. Okay, wax pattern also we are using for the investment casting. So this is a soft tooling. What is hard tooling? Pattern are fabricated by machining either tool steel or aluminum. In this case, a hard tooling we are using a metal. Okay, into the negative shape of the desired components. So this is called the hard tooling. In a soft tooling, we are using a rubber, wax, but in case of hard tooling, we are using metal directly. But in case of hard tooling, this is like a direct method. It means that directly we can develop a tool, directly we can develop the required things. First is called the rapid tooling technique. Silicon rubber tooling. This is also called like a soft tooling also. Okay, there are different types of steps. Just you have to remember the steps so that when once I'll show you the video, the time of the video you will be understood what are the steps are there. Okay, silicon rubber tooling. In the process, molds are made of a silicon rubber material. Steps: the first step is silicon rubber material. As I said, it is comes under the soft tooling, and it is use a material that is called the silicon rubber. Steps: the process involves the making of the master pattern using any available rapid prototyping technique. Okay, we are going to develop a master pattern over here by using any rapid prototyping technique. That may be the FDM or SLA, stereolithography, and any method. Okay, but we have to develop the master pattern. The pattern then finished to the quality in which the final parts are required. Okay, because that pattern is used to develop the number of model. Means pattern means that is called the die, or we can say a mold. It is then suspended in an enclosed box, and liquid silicon rubber is poured all around it. Okay, this set with the time and becomes a solid rubbery mass with the pattern inside the silicon rubbering tool. Now the mold is cut along its patterning time line, and pattern is removed from within. This results in the formation of a core and cavity. Because the material is flexible, undercut release is into a problem. The mold are good enough for 20 to 30 pieces in a material, replicating properties of the thermoplastic. The final process, it means that first you have to make the model by using any prototyping technique, and by that model you have to develop the mold. You have to develop the mold. Okay, you will be understood better in the when once you see the videos, because in the video they have explained how first you develop the model from the RP prototyping, and from the RP prototyping model you have to develop the die, and how you have to develop the die. But that die always used to 25 to 30 parts. That is depend upon the different types of die and different types of material. Okay, See, this is the process actually. Okay, figure has been given. Okay, and we need to make this bottle. So you can see over here, this bottle, first we made, this is a die, this is a die. Okay, this is the master pattern we made by use of any RP prototyping method, and from that we develop this die. Okay, and after this die we will use for the number of to production and fabrication of number of product. Okay, I'll show you the video so that your concept is more clear. Just a minute. If you concentrate towards this video, so that your concept is more clear regarding this soft tooling, as well as how we can develop as well as fabricate a mold by use of a pattern, that is a master pattern developed by the rapid prototyping. So try to concentrate towards this video. Actually this video I have downloaded from the YouTube for the education purpose. It is not for the commercial purpose. You can see this video.
RTV silicone rubber is the most commonly used mold making material, primarily because of its
It is visible to all.
Rubber is specifically known for its superior accuracy, high heat resistance, and excellent tear strength and elongation properties, which is why Freeman offers this line of silicones exclusively. Blue Star silicone rubber is the ideal material for most mold making applications, which is why we will use these materials for all of our remaining casting demonstrations, starting with a simple rubber mold. In preparing a silicone rubber mold, we are first putting clay around the edges of our model to make it adhere to the mold board. Next, we align the model in the center of our mold, remove the sides of the mold, and then press the model onto the wood.
Just a minute. I am looking at video. Oh, just a minute.
Its flexibility and unique self-releasing
You can
properties.
see the video from here so that your concept is
Blue
more
Star
clear.
silicone rubber is specifically
See, this is
known
the
for its
master pattern.
superior accuracy.
Okay, this is the master pattern. This is the master pattern. This is like a silicone rubber we are going to pour into the box. Okay.
Accuracy, high heat resistance, and excellent tear strength and elongation properties, which is why Freeman offers this line of silicones exclusively. Blue Star silicone rubber is the ideal material for most mold making applications, which is why we will use these materials for all of our remaining casting demonstrations, starting with a simple rubber mold. In preparing a silicone rubber mold, we are first putting clay around the edges of our model to make it adhere to the mold board. Next, we align the model in the center of our mold, remove the sides of the mold, and then press the model onto the wood. Next, we cut the excess clay from the edges of the model. Technically, you do not need a release agent with silicone rubber, but in order for the mold to slide off easier, we decided to apply a light coat of Freeman wax release. Here, we are using a white bristle throwaway brush to apply it, and then a cloth to gently buff it. Note that the wood has already been sealed with the wood and plaster sealer, so the surface itself is not porous. Otherwise, the silicone rubber will reproduce the surface of the wood, which is not what we want. For more information, refer to our other video on sealing wood. Finally, we screw on the sides of the mold. And now we're ready to pour the silicone rubber. For this demonstration, we're showing Blue Star's V340 and the CA55 catalyst. The other option here is the CA45 catalyst, which would change the hardness and flexibility. Here is what the base looks like. After the catalyst is shaken inside its bottle, we are mixing 10 parts base to 1 part catalyst by weight, and here is what the mixture looks like. For more information about weighing and mixing, please see our other video on this topic. Once the base and catalyst are fully mixed, we poured the mixture into a larger bucket for the degassing process. Since the mixture will rise while degassing, you need a larger container to hold the silicone rubber. Once it is properly weighed and mixed, our V340 is ready to be vacuum degassed. While degassing is not necessary for lower viscosity silicones such as V330 and V340, after the catalyst is shaken inside its bottle, we are mixing 10 parts base to 1 part catalyst by weight, and here is what the mixture looks like. For more information about weighing and mixing, please see our other video on this topic. Once the base and catalyst are fully mixed, we poured the mixture into a larger bucket for the degassing process. Since the mixture will rise while degassing, you need a larger container to hold the silicone rubber. Once it is properly weighed and mixed, our V340 is ready to be vacuum degassed. While degassing is not necessary for lower viscosity silicones such as V330 and V340, especially for simpler or less demanding casting applications, if you require an optimal, completely void-free mold, we recommend vacuum degassing the material. If you choose not to degas your silicone, you should be careful not to stir the base and catalyst too vigorously, and you should never use a mechanical mixer. When pouring a silicone rubber, you want to pour it at a low point first. Notice that do enter a little more air into the mixture, but these bubbles will break on their own. This mold will take about 16 to 18 hours to cure. An addition cure rubber can be accelerated only by heating it. A condensation cure rubber can be accelerated chemically. Notice the larger bubbles that were introduced while pouring are already breaking on their own. The next day, our mold is ready. We remove the screws and then wedge the whole thing off with very little effort. Next, we pushed out our model from behind. Notice how accurately the silicone reproduces the surface of our model. Next, we pushed out the mold itself and pulled off the edges with our fingers. Our mold is now good for 30 to 150 uses, depending on the material. Anything that gets really hot will shorten the life of the mold. Here we have a mold that is starting to show its age. You can see the absorption of the urethane into the rubber, thus creating a discoloration. While still perfectly usable, this is an indication that the mold is reaching the end of its life. As we pour our thoroughly mixed repro into our mold, we typically like to create a smaller stream in order to break the bubbles better. Regardless, given its thin viscosity, bubbles aren't much of a problem with repro, and it's never necessary to vacuum degas repro. After allowing our part to cure for 60 to 90 minutes, depending on the mass of the pour, we can now demold it and immediately begin using the mold to pour another casting. Even though the repro is hard enough to demold in 60 to 90 minutes, full hardness and strength are not achieved until 24 hours. The part should not be placed into service until then. This mold can also be used to cast other materials, such as an epoxy casting resin, as we're demonstrating here with our Freeman 801. Notice how the aluminum filler used in Freeman 801 will create a little separation of color that you only see at the bottom of the pour. After allowing the material to cure overnight, you are ready to demold. Notice how many of the bubbles stay on the bottom. The thicker viscosity makes it less likely for the bubbles to rise, break, and self-level. However, the surface finish is outstanding. And here we show casting a polyurethane elastomer, such as our Freeman 1060 semi-rigid urethane. This time, we have two different silicone molds created from different models to show how well the silicone transfers the surface features of the original model. The smaller model had a dull finish, that was recreated in the silicone rubber, as well as the shiny finish in our larger model. This little model also displays the flex in our Freeman 1060 urethane elastomer and its superior impact resistance. For complete information on the products you've seen here, plus free access